Hello everyone, welcome to my Cosmology from Home 2023 talk. My name is Jaemyoung or Jason Lee, and I just finished my third year of PhD at the University of Pennsylvania. Today I'll be talking about exploring the non-Gaussianity of the cosmic infrared background and its gravitational lensing. So this work was done with my collaborators from CIB, namely Dick Bond, Pavel Motlock, Alex Van Engelen, and George Stein. This work is now on arXiv. You have the link here. Now, the CIB is not a topic that's very often talked about in cosmology, and CIB lensing even less. However, we believe that the results of our work are not only very interesting, but very important in the context of upcoming next generation CMB surveys. And this is because on top of providing valuable information on star formation, the CIB also biases CMB observations. Additionally, our lensing pipeline can be used on pretty much any 3D intensity fields. Now, what you're looking at here is a patch of the CIB, and at first glance, it looks smooth and rather featureless. Moving on to the contents I'll be talking about today, I'll start out with an introduction, then I'll move on to the methodology. I'll focus extensively on how I lens the CIB. Then I will show you some results. The ones highlighted in bold are what I think are the most important. So what is the CIB? The CIB, or the cosmic infrared background, is the emission of dust from star-forming galaxies. So in these star-forming galaxies, young stars typically emit radiation in the form of ultraviolet or visible, and this gets absorbed by the surrounding dust, then gets re-emitted in the far infrared, and that's the CIB. So it traces galaxy formation, clustering, as well as dark matter. The CIB is broadly distributed from redshift 0 to 4, and the CIB is non-Gaussian, meaning that its power spectrum does not capture all of its information. The CIB power spectrum and the bispectrum has been measured by experiments like Planck, SPT, and ACT. And because the CIB spans 150 to 850 gigahertz, it can be a CMB foreground because the frequencies overlap. Moving on to the simulations that we do the analysis on, it's called the Websky peak patch simulations. So the Websky is based on the peak patch algorithm as well as second order Lagrangian perturbation theory. Once we obtain the halo catalog from peak patch N12PT, the flux of each galaxy is calculated according to a CIB halo model. And this means that the flux only depends on the mass and the redshift of the halo. Then the simulations are normalized such that the CIB power spectrum match that of Planck's. For the lensing convergence map, or the kappa map, we generate it by integrating over the appropriately weighted density field along the line of sight. Moving on to the methodology. As with any cosmic backgrounds, the CIB is altered by gravitational lensing. To make an analogy with CMB lensing, which I'm sure most of you are more familiar with, the CMB can be taken to be a thin shell at redshift 1100 or so, and is lensed by everything between us and the CMB. The CIB, however, gets lensed by sources that contribute to the CIB itself, in an effect called self-lensing. So this means that the CIB at redshift 2 gets lensed differently than the CIB at redshift 3. And this, of course, complicates CIB lensing analysis, which is why we are using simulations for this study. So we split our CIB into delta Z equals redshift 0.2 shells, and we lens each of the shell with its corresponding lensing convergence, like this, to obtain the lensed CIB shells. Then we add up each of the lensed shells to obtain the total lensed CIB map. Moving on to some more details, we use what we call the deflection then magnification method. And we adapted this method because conventional CMB lensing software proved to be insufficient for our uses. But before we do the deflection and magnification, we first smooth our kappa maps with a pixel-sized beam in order to mitigate strong lensing. This is because we have quite a few kappa values that are larger than 0.1 or so. Then we deflect the galaxies by an amount given in standard equations. Then we magnify the galaxies by mu equals 1 over 1 minus kappa squared minus gamma squared, rather than the often used approximation factor 1 plus 2 kappa. And this is because even after the smoothing, there are still a non-negligible number of pixels that are quite large. Here is an animation depicting our deflection then magnification method. Here are some more visualizations. On the left, you're looking at the kappa squared, and you can see the clumps of matter. On the right, you can see from the gamma squared map that the gamma squared traces the cosmic web structure. Here are some more characteristics about our CIB maps. And on the top, you're looking at the CIB flux in slices. And you can see that the peak flux is between redshift 1 and 2. And this is because the key star formation region is redshift 1 to 2. In the middle, you're looking at the lensing kernels. And on the bottom, you're looking at the RMS deflection angles for the CIB. And you can see that on average, the CIB RMS deflection angle is about 1.3 arc minutes, which is about half that of the CMB lensing deflection angle. And you can also see that in our analysis, the very first shell is not lensed. Here is how we quantify the filter statistics. I'm sure all of you know that the variance is the fluctuation squared. The skewness is defined as fluctuations to the third power, while the kurtosis is the fluctuations to the fourth power minus this factor in order to ensure that the kurtosis becomes 0 for Gaussian map. So we band filter our CIB maps, and we calculate the statistics within each L band, and this corresponds to its respective polyspectra. Here I'm showing you the equations for completeness for our 2-point and 3-point and 4-point statistics. For the 2-point and 3-point, the calculations are relatively straightforward. For the 3-point and 4-point, we are probing primarily the roughly equilateral configuration. The binning is as given here, and it takes about 8 minutes on the Niagara cluster to run our filtering code. Moving on to some of our results. First, I'm showing you how our unlensed Websky CIB statistics compare with that of Planck's. So from the left is the 2-point, 3-point, and 4-point. You can first see that our power spectra values match pretty well with that of Planck's, but this is of course partly because it's been designed to do so. But in the middle, you'll see that our Websky bispectra values match Planck values pretty well as well, and this is very non-trivial because we have not induced any non-Gaussianity parameters into the simulations. Also, the caveat here is that in order to exclude the very bright nearby sources, we are using flux cuts, and we're using the same values as Planck flux cuts. Also, you can see that in the low L regime, you're looking at the clustering part, while in the high L, you can see the flat Poisson tail. Here's the redshift breakdown of the CIB statistics. And you can first see that most of the CIB statistics come from redshift 2.5 or below. And this is because the key star formation region is redshift 1 to 2. You can also see that for the 3-point and 4-point, there's actually a large contribution from low Z, especially at high L. And this implies to us that the bright nearby sources and hence flux cuts can be important for the change in 3-point and 4-point in particular due to lensing. And here is how lensing affects the CIB statistics. On the left, so I'm plotting the quantity ratio to unlensed -1, you can see that the power spectrum changes minimally, about 1.5% or so, and this is as expected in previous work, while the 3-point and 4-point actually increase substantially, especially at large scales. You can also see that there's a more frequency dependence for the 3-point and 4-point, but we believe this is because of our flux cut choices and not something necessarily physical. Now let's look at our 3-point comparison with Planck again. And you can see that our lensed Websky values are slightly closer to the Planck values than before, So we believe that at least part of the reason why the unlensed Websky bispectra values are lower than that of Planck's is because of lensing. And here's what happens if we do the lensing in different ways. So on the top panel is when we change the magnification factor. And you can see that in the blue bold, when we use the proper magnification, the results are pretty different from when we use the approximate magnification factor of 1 plus 2 kappa, shown in red. Also, on the bottom, you can see what happens depending on how we treat our kappa maps. So again, in the blue bold is our default version, smoothed by a beam, a pixel-sized beam. And in the red and the green, you can see what happens if we set a hard kappa max of 0.1 or 0.3. And also in teal, you can see how the statistics change if we do not treat the kappa map in any way. I'm sure all of you enjoyed our results up to now. So the plots on the 3-point and 4-point statistics of the CIB. But even the 3-point and 4-point statistics do not capture all the non-Gaussian information the CIB has to offer. So how do we go beyond endpoint statistics in order to capture as much information as possible? The answer, of course, is histograms. And on the left, you're looking at the unlensed and lensed CIB histograms plotted on top of each other. But here, you can't really see much of a difference. But when we take the difference between the two, you can see this clear oscillation structure. So what do we do with this? What we decided to do was to use a quantity called relative entropy, which is quantity motivated from KL, or Kullback-Leibler divergence. And I'm sure a lot of you working on machine learning are familiar with this quantity. But it's a way to compare two distributions, P and Q, and it's given as the sum of P log P over Q, where P and Q are probability distribution functions. So what we did was to plot this relative entropy quantity. There are two versions for us, the unweighted, the equation given on the Y label, and the weighted version. So on the top are the number of standard deviations away from the mean of the unlensed. And on the left, you can see that for the unweighted relative entropy, when plotted for each of the L bands, they probe basically the tails of the PDFs. But in the middle, you can see that for the weighted relative entropy, you can now probe the regime closer to the mean of the PDFs. So what can we do with this? So what we thought we could do is to use this equation over here and use a combination of the data and simulations in order to plot a spectra of Q-lens CIB parameters, given some initial intrinsic CIB parameters as well as the lensing amplitude. Then what we can do is we can tweak these parameters and iterate until this spectrum of Q-lens CIB becomes flat in order to constrain both the CIB intrinsic parameters as well as the lensing amplitude. Moving on to some plots on the cross-correlation between the CIB and the CMB lensing. On the top here, you're looking at the unlensed CIB cross-correlated with CMB kappa, and in green, the lensed CIB cross-correlated with the CMB kappa map. And on the bottom, you're looking at the ratio between the two, and you can see that at L equals 2000 and above, the ratio rapidly diverges from 1. But how come we have not detected this yet? On the right, I'm showing you the plots where we have overplotted the Planck error bars, and you can clearly see why we still have not detected it yet. But we believe that the story could be potentially different for Simon's Observatory and CMBS4, where the precision is much better. I mentioned towards the beginning of this talk that in our Websky simulations, the flux of the galaxy depends only on the mass in the halo model. And this, of course, is an approximation. In order to make things a little more realistic, we tried to model for some of the environmental effects that might occur within a galaxy. We multiplied the flux of each galaxy by this exponential factor given here. Then we normalized the map such that the power spectrum matches Websky values at L equals 500. Here are our results, and you can see that the 2-point and the 4-point statistics change slightly less compared to the 3-point. What we had initially hoped to do was to be able to increase the 3-point spectrum at low enough L so that it matches that of the Planck values even better than before. But we found that because we have the power spectrum anchored at L equals 500, this is not possible. However, with future observations that have higher resolution, going up to higher L, we believe that the observations might have the potential to distinguish between different stochastic models. In conclusion, we've first shown that the Websky CIB maps capture the bispectra, in particular the equilateral bispectra, reasonably well. We also showed that the CIB lensing increases the power spectrum by about 1.5%, so pretty small, but the 3-point and 4-point by 10 to 20% or even more. Third, we've shown that the relative entropy is a quantity that can be used to probe both intrinsic CIB parameters as well as its lensing. Next, we've shown that CIB lensing could potentially be detected through cross-correlation with CIB lensing. And lastly, we've shown that inducing stochasticity can change CIB statistics. So why do we care? As mentioned in the very beginning of this talk, CIB non-Gaussianity provides extra information on top of the power spectrum. Also, our lensing pipeline for the CIB can be used for any 3D intensity fields such as 21 centimeter, Lyman alpha, and other millimeter wave intensity fields. Third, CIB non-Gaussianity has been shown to affect the detection of primordial non-Gaussianity, so it'd be great to have a better understanding of CIB non-Gaussianity. And lastly, the change in CIB non-Gaussianity due to lensing could be important for next generation surveys. Thank you very much.